All right, so our next speaker is Josh Taylor. Josh Taylor is one of our Cosmic AI postdocs. He's been at UT for a few years. And before that, he got his PhD in statistics at Rice University. So today he's talking about time series modeling of high resolution radio spectra.
Yeah, thank you. It's always a little disappointing to have the statistician follow the pretty picture guy, but we'll work with it. So yeah, this is kind of a modeling issue, and it's something that came up in conjunction with a totally unrelated task earlier this year, so I spun it off as a little bit of a side project. But we're going to talk about time series modeling for radio spectra, and really it's probably applicable to any sort of high resolution spectral setting. But in particular, we're going to talk about what can we tease out of the error modeling from this, right? And the goal is sort of how can we better distinguish things that we might believe are sort of more pure emission or absorption signal from other things that might be structured contaminations of the spectrum. Sorry. Okay, so I'm going to present kind of the setup and this modeling technique all in the context of Orion. So I thought I would just get that out of the way. So we're going to use ammonia emission from Orion. This was as part of the Green Bank ammonia survey, so image of Green Bank. It's not a huge cube, medium resolution, but everything you see here today will be in the context of ammonia 1.1. And I picked Orion because there's a lot of known YSO activity in Orion, and it contributes to something I'm going to call the mixed source problem in a minute. So we'll just see how that plays out. Okay, so originally I said this was sort of a spin-off of something else. So I primarily work in clustering, in particular clustering these cubes. And radio cubes are noisy, right? So when you apply any clustering technique to this, you're just going to get like more clusters than you want to deal with. And so fine, we've got my clustering of Orion. We won't talk about how that appeared. Just it dropped out of the beautiful sky, false colored. And then on the right, I've plotted some of the mean cluster spectra for these regions, right? So this clustering was done only with spectral information. The spatial coherence appears solely based on spectral coherence, right? And so, I dutifully produce all these clusters, and then I take them to, the observers here, and they say, well, what are these clusters? What are they capturing? But again, this stuff is noisy. And I guess I took a pause and stepped back and just thought, well, did I cluster noise? And if so, how might I be able to detect that, or at least prioritize it such that I don't send some astronomer's valuable time down a rabbit hole, right? And so in order to do this, I took an approach of just trying to better understand what types of error we could characterize in these spectra, and then we'll see how we go on from there. So I thought I might play a game that I'm calling the spectrum is right, and so we can we can kind of talk about how so in my world, astronomers seem to be very focused on sort of, and I would say intensity-based metrics of a spectra's and like informativeness, right? Is this real or not? Is the signal to noise ratio high? But a statistician approaches this a little differently, right? Because there's like an explicit consideration that there could be correlated structure in this process. So we view it more as like a process instead of just, an appearance of independent intensities. So this spectra right here, it comes from a bright region. I've tried to plot it. It might be too small, but I tried to plot the spatial location up in the Orion map and as a red dot. So this spectra corresponds to that red dot. And it's in a bright region. It's got a visibly pronounced structure. It's got a high signal to noise ratio. And the statistician says, and also if you apply a white noise test to this process, we totally reject this assumption that this structure is independent channel-wise, right? So great, we both agree in this case. But on the other hand, this spectra would I would say mildly pass sort of an astronomer's smell test. Like, I mean, I see SNR3 thresholding sort of all across the board. So you can, we can play with the thresholding, but the story is the same, that there are spectra that have higher signal to noise ratios, but that don't pass a statistical test, a smell test of structure, right? So this fails to reject this white noise test. And so a statistician says this is just mess. Astronomer says, oh, higher signal to noise, so I'm going to roll with it. And then, kind of on the other hand, we do have instances where we've got lower signal to noise, but the statistician says, okay, wait, there is still something happening here, right? So there is some process. And so the point of this is to try to reconcile some of this, or at least provide an alternative explanation for some of these differences. And in particular for me, when I'm trying to say, prioritize some kind of workflow for all the analysis that's going to happen downstream, right? Okay, so yeah, I said that I was calling this the mixed source challenge, and it's basically predicated on this assumption that in any spectra, there's sort of genuine signal that we're trying to uncover, but that there's also many sources of what I'll call structured contamination, right? And that's contamination or error that perhaps doesn't exhibit characteristics of just random white noise shocks, right, to the spectrum. So we're going to try to do this cohesively, to make these considerations simultaneously. The problem is that all this stuff gets entangled in the observed spectra that we see, right? So, I would say I've used maybe charged words or contamination, but, structured error, maybe that's a more politically correct way of saying, can have high signal to noise ratios. And conversely, real signals can be weak, and so how might we proceed to disentangle some of this stuff? And the way we're going to do it is, or the way that easiest way that I could think of to do it was to go back to time series land, right? And so time series this is very old stuff. I like to say that this is the latest iteration of my, I guess, nostalgia period this year, where I'm trying to squeeze new things out of old tools. But yeah, we've had a couple of talks just a couple of weeks ago applying sort of time series type logic to spectra, so I don't feel like I need to totally introduce that. But just to point out that it is a statistically principled framework for some of the structural modeling. Okay, so ARIMA is pretty much the workhorse in this domain. It's been around a long time. Lots of stuff, depends on it. And ARIMA stands for AutoRegressive Integrated Moving Average Modeling. And it's kind of a mouthful, which is why we have that acronym. But the point of it is to simultaneously model persistent structured signal and structure that could arise from a noise process, in addition to sort of the random shocks that we would consider standard. And when we do this type of modeling, a couple of things just fall out on the table immediately. One of them is sort of fitted values from this modeling. So whatever you were going to do with the spectra, you can just plug the fitted values in and run with it. And I've tried to keep that part very generic because I don't know what you might want to do with the spectra. But more importantly, and I think what I'll spend more time talking about, is just building this evidence for maybe like a bit of decision making, a more principled decision making about is the structure I see due to some sort of persistent pattern that I think might be interesting or useful to dissect later, or could it have resulted from error, right? And so the way we model this stuff obviously influences the answer to that. So we'll see both of these like in the context of Orion in a minute. But first, I wanted to maybe, I don't know what everybody's starting point is here. And frankly, before this, I had sort of forgotten all the details of ARIMA, so I have to remind myself anyway. But ARIMA's got two components, the AR component, the autoregressive part. And these are typically denoted an AR model of order P, which just means that the the value that you see at time t is dependent on the values that you see from time t minus p, right? It's like super simple linear model. This type of, or this branch of the ARIMA equation Picking out sort of these longer term persistent patterns, would be better for like broader type emission, or smoother spectral features. Something that I would say more closely aligns with an emission profile. And so on the right here, we've got a kind of a synthetic, purely autoregressive process that I just made up. This is AR order 2. And then below that, you've got these sort of standard tools in the statistician's diagnostic toolkit. When you approach this sort of time series modeling, you look at what's called the autocorrelation function and the partial autocorrelation function. But the behavior of those things, we don't need to get into it, but that's very indicative. What you see there, the smooth decay in the ACF and the sharp cutoff in the PACF is very indicative of the existence of this longer term process, persistent memory. Okay, so the second part is what's called the moving average component. And this is kind of the same thing, but the idea is that the current value that you see is just completely linearly dependent on some order Q of the previous error innovation, right? And so this would be, applicable more in cases where you've got some kind of like shorter term shock to a time, or in case of wavelength or a frequency or whatever that might have appeared from various provenance. But these, and again, these ACFs and PACFs are pretty indicative of moving average models. But the key point here is that it's trying to capture error that might be systematically related to each other, right? So if there is some structure that we observe that could be explained by error, well, let's do that and then remove that, right? And so, yeah, we're trying to account for both. And when you put all this together, you get the full ARIMA PDQ model. And the D parameter is just there to sort of satisfy some assumptions of the AR and MA models independently, but essentially you can't have like a linear trend and fit this ARIMA model. So the D just differences out, tries to remove linear trend as best it can before it does the fitting. And on the right again, you've got this kind of, I think it's a 202 process, so no differencing needed, but it's got kind of a second order dependency on previous values and previous errors. And so you get kind of a mix of these things. And, by allowing or considering acknowledging that you can have both of these types of effects influencing a velocity structure that you see, we're able to maybe model some more complex structure a little bit more in a more refined way. And that would be the goal. Okay, so how do we fit this? This is pretty much always based on information criteria, just in an effort to be parsimonious. And you choose some maximum value for the order of the AR and the MA components. Given that we're in this sort of radio setting, I've pegged those at like the full width half max of the moment 2, basically, of the spectrum. But the upper limit here doesn't really matter too much because there's been a lot of work creating these stepwise search procedures so that you don't actually have to do a full combinatorial grid search for these parameters. Okay. So the point of all this is just that it's a pretty fast process. It doesn't take a lot of time. And I'm like totally glossing over the mechanics of this fit, but this is standard like de rigueur in like any processing or programming language. Okay. So one thing I did want to point out was that typically ARIMA is used in the context of forecasting time series, and that's like very much not what I'm doing here. I mean, part of the reason is that it just doesn't make sense to be forecasting, outside of like whatever frequency range that we're considering. And so, yeah, we're not going to do this. We're really doing this for understanding or explanatory reasons, for me to try to have better informed decision making. If I tell somebody, hey, I think this is useful, you should spend time on it, or no, you might could leave that on the shelf until you've got some free time or whatever. And so, yeah, the result will be understanding, and that we're going to sort of tie these AR or autoregressive terms to kind of persistent, we hope is emission, source emission behavior. And then the MA terms would be assigned to sort of structured inference, right? So it's the same framework, same math, just different goal, right? I'm not ever going to forecast. Okay, so what do we get from all this? Okay, so this would see, I would say, like result number one, which was not really the goal of this. I just put it together to kind of have a sanity check here. But on the left, on the x-axis of all the scatters on the left, these are sort of published summaries of all the pixel spectra that's in this Orion cube, right? And these are published along with the ammonia survey. And so you can just go pull them and look. On the y-axis, you've got sort of these fitted, ARIMA fitted values, ARIMA fitted analogs of these values. And the main difference in general, which we can see on the right, which compares sort of the raw, or say, published moment zero with this inferred moment zero or fitted moment zero, is just that we've toned down flux, particularly in, I would say, these off filament regions. And so things are kind of coming, the filaments are shining, I would say, stronger relatively, and you know, kind of the off stuff is toned down a little bit. And the way that, you know, the reason for that is that we've essentially allowed flux to be contributed to an error process, right? So spectral intensity can now, you know, it has a place to be attributed to other than just emission of the source. Right? And so this is, you know, kind of an eyeball test. And if there's time at the end, I can talk about some possible peculiarities or possible like great things about this. I'm still unsure what they are. But the point is just that by allowing a little bit more flexibility in our error considerations, that we can get, you know, cleaner things. And in particular, we're doing this without sort of component, like standard component fitting, or maybe going off source to estimate noise. And I'm not going to say that this is like a replacement for component fitting, like that obviously has a role. But it could maybe help you decide whether you should even be trying to fit components to a certain pixel. Like if some pixel is just deemed kind of noise dominated, then it might not make sense to do component fitting or inference from that fitting. But the other thing is that ARIMA explicitly considers and accounts for you know, channel adjacent correlation in this process, whereas Gaussian component fitting doesn't. So it's just, you know, fit a shape. So yeah, that's kind of product number one, but you know, benefit, but not necessarily the point. And from the beginning, you know, the main motivation for me was just trying to more definitively tell this observer that imaged Orion, help point them, I would say, maybe it's a better way of saying it, to interesting regions, signal regions of this image versus noise-dominated regions without appealing totally to intensity metrics. And so, or with, rather, considering the structure, velocity structure. So the approach here is that we're going to fit a full ARIMA model, and then we're just going to go into those separate components and see, kind of compare their goodness of fit criteria, right? And say, well, if we find a spectra whose fit is predominantly driven by the autoregressive part, then we think there's kind of a persistent longer term pattern that maybe we should, you know, consider. If it's primarily driven by the error part, then, you know, we'll figure out what to do with that in a minute. But in order to do any of this, we're going to have to maybe do the boring part and and define a statistic and look at its distribution, right? So what I'm calling my signal evidence statistic is essentially just the difference in the AICs and the fit criteria of these individual models, right? So if I fit a full ARIMA PDQ, then I fit an ARPD and an MA-DQ, and I compare the fit. And this has been centered and standardized in a certain way that I'll get to in just a second. But just think of it basically as just the difference in goodness of fit. And remember, well, in this context, sometimes there's different interpretations. But in this context, I'm using the AIC, and lower is better, right? So that's kind of standard there. And so according to this statistic, any of this delta AIC that's like negative says, oh, the AR model fits better. Positive, the MA model fits better. If it's zero, I can't tell. And so in order to, I would say, statistically say less, greater, equal to zero, then we need a distribution of this thing, right? And so the reason I wrote it this way is that if you do the algebra here, plug in what the definitions of AIC and subtract off that, and normalize, scale by a particular value, we know the distribution of this. So, this basically devolves into a log likelihood ratio, which would be standard and kind of stat 101 if these models were nested, but the ARP and the MAQ models are not nested, so we can't just appeal to sort of base statistics, but there is this more exotic version of the likelihood ratio test that we can invoke. But anyway, the point is that we can get a distribution around this thing. And the scaling factor can be estimated from the likelihoods of the data that you see. So we've got all the components to do this. So when I do this, I get this statistic, and in this setting, you might otherwise go and say p-value, p-value, p-value. So I've produced a p-value like quantity, but I'm not really going to hard threshold in sort of a binary yes or no on it. I mean, first, I just wanted to see sort of the gradient of this, like what does it look like? And so I'm calling this sort of probability of, signal, I guess is the right word, a signal confidence, right? But there is a little bit of subtlety we need to address, which is that ARIMA modeling kind of has severe identifiability issues. This is known, this is not new. It doesn't just exist in this setting, it exists everywhere. And like as an example, you could have two AR order, an MA order of 1, but that might fit almost as well as just a AR3 or an MA2 or whatever. And part of this can appear if you over parameterize these models, that you can start kind of down this rabbit hole of like, oh, if I add one more AR term, then I get a little bit better. Oh, but then if I add 2 more MA terms, I can match that. And so I would really rather not sort of force. So my solution to this is just to not force a decision, right? So I'm going to allow some range of this signal confidence to just include or denote pixels for which I can't tell, right? There's ambiguity. Maybe I screwed up with modeling. Maybe the data is just not really supportive of either of the regimes. But in any case, I'm just trying to be a little bit more honest here and say, well, there's some that I can tell you, like, go for it, spend your time here. There's others I can say, I don't know. And some in the middle, I would say, end up with a maybe, maybe something useful there. So what does this look like for Orion, right? I have taken the liberty now, once I produce this sort of continuous signal confidence value, I then clustered the distribution of those values because I've predefined these tranches, right? Sort of signal, structured noise, or an indeterminate region. So instead of just arbitrarily putting cutoffs on this distribution, I just clustered it. And when I do that, I end up with sort of the S, the dark purple signal dominated stuff. It's like about 40% of what's in Orion. And these things have higher confidence that there is persistent pattern in signal, right? And the signal very much kind of occupies the filaments. So great. If it didn't, I would think this is a little bit weird. There's white noise. So that would be stuff that does not, even get out of the white noise test stage, right? So that stuff I think can more or less just be taken off the top and set aside and probably ignored forever. There's structure noise, which might be useful, I don't know, to say something about perhaps the cloud around this core or something like that. So there would be influences, persistent or structured influences from, I don't know, something, interference, environment, whatever it is, but at least you kind of know which direction you're headed there. And then, this indeterminate region, which it's maybe hard to see, but typically is right on the the bulk of it is around the edges of the signal region, so that makes sense. Okay, so just to wrap all this up, we've got some kind of maybe more flexible modeling of spectral structure, and possibly some new denoise data products for downstream science, but there's other ways of denoising, so I'm not championing that as strongly as I am this sort of more principled view of signal importance or signal usefulness. And then also, just this idea that when we don't know, we just admit that we don't know and not try to force, not try to force them. So that's it. Yeah, sorry for all the statisticians like null distributions. So sorry.
Problems on how this may be used out of this.
Yeah, I mean, well, anything that's so really what you need here is some, you need, I would say, higher resolution. So you can't do ARIMA modeling with, I don't know, a series of size 10. It just doesn't really make sense. And you also need, this assumption that the x-axis, time, frequency, wavelength, whatever it is, that there would be correlated behavior in adjacent regions along that axis. So if you ever end up in a situation like that, something like this could be applicable. I mean, if there's time, I can show something else that's. Oh, okay. Can I hear? Brian's mic doesn't work today.
Sorry, did we, can you hear us?
Yeah, I can hear you.
Okay.
Yeah, thanks, Josh. It was super interesting. I'm curious about whether the data that you're looking at here has already been baseline subtracted. Like, is this raw GBT data from GAS, or is this already pre-processed data? And building on top of that, I'm wondering whether there's implicit assumptions being made here about the width of the features that are like sky emission features versus contaminating features, because there's like large baseline ripples, for example, in raw GBT data that would have what I think would be AR type behavior, but they're actually contaminating structure. And so I didn't quite understand how this framework would work when you have either very narrow lines or very broad lines, or different types of contaminating structure and the relative widths of each of those different features. So maybe if you could comment a little bit on that and where it's applicable or where it's not, or maybe that goes into the number of terms that you have.
Yeah, so I do think this data has already been pre-processed to remove some of those ripples. What you bring up, I think, is valid in the sense that there are real things you might be interested in that behave. So I've kind of simplified the discussion of this and said, oh, AR terms represent real stuff and MA terms represent, nuisance stuff. That's not necessarily always true, right? Like if you do have a reason to believe that the behavior you're interested in is better modeled by sort of a shorter term memory shock to the process, then you could fit it. And instead of, concluding that the MA terms are nuisance, conclude that that's actually what you're looking for, right? And then focus on the fit there, right? So that's like the framework would stay the same, but it would depend, which branch you're interested in might depend on some assumption you have about width or whatever. Does that make sense?
Thanks. I think TMC1 would be a really interesting counterpart to this, where it's got very different sort of extremely narrow line widths, and so it might be a really interesting counterpart to Orion in that sense.
Yeah, and I mean, one thing I will say is that there's nothing, if you have a good guide to maybe split your full spectra up into maybe more local regions, then there's no reason you can't apply the same thing locally, right? And then
Yeah, okay.
to that point as well, there are also add-ons you can make. Like there are statistical processes that allow for a heterogeneous channel-wise variance. So you might in regions, have an RMS value for certain wavelengths that is higher than for others, and there are ways to handle that. So locality, could influence this for sure.
Super interesting. Thanks.